This is static electricity. And this is static electricity. Here's another example of static electricity. Static electricity can be a nuisance. Static sparks can cause fires in homes as well as in industry. Yes, static electricity is a phenomenon of nature that has been with us longer than the man. Since ancient times, scientists have studied static and conducted experiments to find out its characteristics and its hazards. Now, let's see a few of the laboratory experiments presented in the Bureau of Mines demonstrated lecture on static electricity. First, meet Mr. G.M. Kintz and his co-worker, Mr. H.F. Brown, both of the Bureau of Mines. Static can be generated by rubbing two materials together, but rubbing is not always necessary. When the metal disc is placed on the plastic plate and lifted, it takes a charge with it and leaves an opposite charge on the plate. Static electricity is generated by the contact and separation of materials. Static electricity generated as the metal disc is lifted from the plastic plate flashes the fluorescent tube. It takes about 10 volts of static electricity per inch to excite a cold fluorescent tube. To understand how static sparks can cause fires and explosions, we must know how fire is created. Fire must have a fuel. Substances such as gasoline, benzene, kerosene, and even wood, however, will not ignite. To use them as fuel, they must first be in the form of vapor or gas. But vapor or gas alone won't burn. We must add air. We know that it is the oxygen in the air that supports combustion. The third leg of our fire triangle is heat. In addition, these ingredients must be mixed according to a very definite recipe. We must have a definite ratio between fuel and air. This ratio is known as flammable limits. For example, acetylene will burn or explode only if its concentration is between 2.5% and 81% by volume in normal air. Each flammable gas has its own flammable limits. The flammable limits of natural gas are between 5% and 15%. Any percentage greater or less in normal air will not propagate flame. As we talk about static, we are talking about the heat leg of our fire triangle. We normally think of heat as the heat given off by a flame or generated by an electric filament. In discussing static electricity, however, we should think of heat in terms of concentrated energy, electrical energy, often so small that you will not see the spark. Physicists tell us that this amount of energy is approximately what a fly would expend in walking a few inches up a wall. This tiny amount of energy expended in the form of an electrostatic spark will ignite flammable mixtures, such as the one in the explosion tubes you have already seen. This tube is first flushed with air or oxygen, and then a small amount of flammable fluid is added. Now let's look at another Bureau of Mines experiment. It demonstrates how static can be generated in one area and then induced on insulated objects in another area, where a spark can cause disaster. This Van de Graaff machine consists of a belt running over two plastic pulleys. The contact with and separation of the belt from the pulleys generates static electricity on the takeoff side. The metal ball accumulates the charge. To illustrate induced charges, Mr. Brown moves the explosion tube toward the machine generating static. Charges induced onto the ball terminals of the explosion tube caused the ignition. To cause a spark to jump that distance, the machine had to generate thousands of volts. If this relatively small ball accumulates a charge of that magnitude, think what tremendous charges accumulate on thunderclouds. Consider this example of an accident probably caused by an induced charge. A workman was filling a tank truck with a low vapor pressure flammable liquid, while small thunderclouds were passing overhead. Sparks occurred and ignited the vapors at the hatch. When engineers investigated, they found that the man, the tank truck, and the fill pipe were properly bonded and grounded. They discovered, however, that rust, paint, and other materials insulated the hatch cover from the truck. It is believed that as the thunderclouds moved away from the area, the induced charges on the man, the truck, and the fill pipe could leave and follow the clouds. The induced charge on the hatch cover could not. When there was enough difference of potential between the hatch cover and the tank truck, a spark occurred. Other examples are accidents in geophysical shooting and blasting operations. Many premature detonations have been caused by static charges induced onto electric blasting lines by thunderclouds. When the wires of an electric detonator are thrown into the air or strung out, they act as an antenna and collect charges from thunderclouds. If it is not a static resistant detonator, a spark can occur in the detonator, causing a premature ignition, even though the wires are short-circuited. The detonator is fired by a spark that occurs between the bridge wire and the copper shell of the detonator. Let's see exactly how one of these premature detonations takes place. Mr. Brown places a live detonator in a heavy steel jacket. The lead wires are short-circuited. A sufficient charge will be induced in the line to fire the detonator when the lead wires are thrown near the static machine. When there are thunderclouds in the vicinity, blasting operations should be stopped. Because of their safety features, only static-resistant detonators should be used where there may be hazards of induced charges. Static is always generated by contact and separation. So liquids falling through space and breaking into droplets generate static. The best way to prevent falling liquids from generating static electricity is to extend the fill pipe to near the bottom of the tank and get subsurface discharge. Lubricating oils and most hydrocarbons in pure or semi-pure state are poor conductors of electricity. But what about liquids that are good conductors? Mercury is one of the very best liquid conductors. Let's see whether falling mercury will generate static. This mercury dropper consists of two funnels. Small holes in the plug at the end of the stem of the top funnel allow the mercury to spray into the bottom funnel. This wire connects the mercury in the dropper to the explosion tube. It makes no difference whether the liquid is conductive or not. When any liquid falls through space and breaks into droplets, static is generated and can accumulate on any nearby insulated conductive object. To prevent this hazardous accumulation, bonding is the answer. Now, as mercury flows through the funnels, no explosion occurs. Even water, by forming into droplets and falling through space, can generate a static charge. In fact, the greatest manifestation of static in nature, lightning, is generated in this way. This Kelvin water dropper consists of 4 empty cans with the tops and bottoms removed. There is a screen in each bottom can to collect the static. When water flows out of these nozzles and falls in droplets through the cans, sufficient static is generated to ignite the explosion tube. This small amount of falling water is all that is needed to generate enough static to explode a flammable mixture. Many other liquids are just as effective. Mr. Kintz will show us what happened in an ammonia manufacturing plant. A water solution was flowing into the top of a large tank containing a flammable hydrogen mixture. An explosion occurred inside the tank. It is believed that the water solution flowing into the top of the tank created the static that caused the ignition. Many people are under the false impression that humidity stops the generation of static. Just remember that our strongest manifestation of static occurs during thunderstorms, when we often have our highest relative humidity. High humidity does not stop the generation of static, but it can prevent the accumulation of static. Mother Nature does with humidity what should be done mechanically in industry. With a microscopic film of moisture, she bonds all surfaces together electrically, so there is no difference in potential. When 2 objects are bonded together, there can be no difference in potential and no spark can occur. Before you pour flammable liquids or permit them to flow from one container to another, be sure that the containers are electrically bonded, unless it's a closed system. A workman in a refinery was doing exactly what Mr. Brown is now doing, except the 5-gallon can and the metal funnel were not bonded together. Static generated by the falling liquid ignited the vapor. Because it is not possible to bond glass containers electrically, the liquid should flow in a smooth stream. Do not hold the container in the air and let the liquid break into droplets as it falls. In dry weather, when a man walks while wearing heavy woolen or synthetic clothing, the layers of clothing separating from each other may cause a heavy charge to accumulate on his body. You've seen liquids fall through space and generate static. Now, how about solids? The 2 pieces of tubing held by Mr. Brown are insulated from each other by a plastic ring. When air at low pressure is blown through the tubing, nothing happens. A clean, dry gas at low pressure does not generate static, because there are no solid or liquid particles present to contact and separate. When a tiny amount of dust is added to the air, a sufficient charge is generated to cause ignition. Moisture, dust particles, rust, and other impurities can contaminate natural gas and make it a static generator. This equipment demonstrates how fires have started while sulfur was being loaded into a ship through chutes or piping. Using this equipment, Mr. Kintz and Mr. Brown have tested flour, rust, sulfur, coal, grain, catalyst, and many other materials. They all generate static. If a high-pressure gas line ruptures, many people think that mechanical sparks or heat of breakage ignite the gas. But these conclusions are often doubtful. The probability is that the escaping high-pressure gas creates dust clouds, and the dust particles generate a static charge which ignites the gas. To purge the oil compartment of a barge, carbon dioxide was turned into it. The carbon dioxide snow striking an insulated conductive object created a static spark, which ignited the vapors. As a truck travels along the highway, it accumulates a charge in 2 ways, from the dust in the air contacting and separating from the truck, and from the tires contacting and separating from the pavement. This miniature truck has been given a static charge. Here's what can happen when it backs up to a tank which is leaking flammable vapors. This hazard can be eliminated by the proper bonding and grounding of the truck before opening the fill caps. With everything bonded together, there is no difference in potential. Now, when the truck approaches the tank, no spark can occur. Drag chains, belts, or wire on trucks or planes are seldom effective in removing static charges. This truck is not being grounded at all because asphalt, blacktop, and dry concrete are all insulators. Tremendous static charges can build up on a flying plane. An uncharged plane taxiing across a dry concrete or blacktop runway can accumulate a charge. Refueling crews are well aware of the hazards of static electricity. That's why they first ground the truck. Then the truck is bonded to the plane. Finally, the nozzle is bonded to the plane before opening the cap of the tank. Lightning is nature's greatest manifestation of static electricity. It is generated, of course, by contact and separation, or by rupture and separation of raindrops during violently turbulent conditions. As charged raindrops fall to Earth, they leave one charge in the cloud or atmosphere and bring an opposite charge to Earth. After enough raindrops have fallen, the difference of potential between Earth and the cloud becomes great enough to cause a stroke of lightning. Lightning can discharge from a cloud to Earth, from Earth to a cloud, or from cloud to cloud. As the cloud passes through the atmosphere, the opposite charge follows it on the Earth. When the cloud passes over a tall building or other high objects, the gap is narrowed and a stroke may occur. Then, too, when a cloud passes over a building or structure, there is an immediate rush of charges to bring everything to the same potential as the Earth. Under certain conditions, sparks can occur between insulated objects. When oppositely charged clouds are neutralized by a lightning stroke, their earthbound charges must neutralize themselves. In so doing, they may form an arc between insulated objects or between insulated objects and the Earth. This arcing is one of the reasons why bonding should be used between all machinery, pumps, pipelines, and other conductive insulated materials. This building might represent a gasoline transfer pump house or a chemical process building where flammable material is being vented. The discharge ball can represent a thundercloud. When lightning strikes, we have a fire. Some gases lower the dielectric strength of the air, and very often the structure venting fumes will be the one hit. Mr. Brown sets the cloud at a distance where the lightning will not jump. When gas is released, the lightning strikes the building by following the weakened path created by the gas and causes ignition. The protection for this building is lightning rods. Now, as we bring the cloud right down over the building, there is no stroke of lightning. The points bleed off the static charge faster than it can accumulate. To be effective, lightning rods must be properly designed. There must be several air terminals. The terminals must be high enough, properly spaced, and connected to a properly installed ground conductor of the right size. Improperly maintained lightning rods may become hazards. Broken downcomers or discontinuity anywhere can cause secondary sparks. Remember, when a stroke of lightning occurs, millions of volts and thousands of amperes are released in milliseconds. When a pipeline that might release flammable materials is opened, a stray current, static discharge, or lightning discharge might cause a spark and ignition. A bonding cable should be put across the gap to bond the two sections of the pipeline together. You have seen that static electricity is generated by the contact and separation of materials. You have seen how a tiny amount of energy expended in the form of an electrostatic spark can ignite a flammable mixture. You have seen how static can be generated in one area and then induced into another area. How falling liquids generate static, whether they are conductive or not. How even water can generate static. How falling or flowing solids can generate a sufficient charge to cause an ignition. And how static charges can be carried from one place to another on an object or a person. Remember that the dangers of static can be minimized by filling tanks from the bottom up to get subsurface discharge, by properly bonding and grounding, and by proper use of lightning rods. Static is not something to be afraid of. Knowledge of the hazards of static electricity and knowing how to control them will help prevent accidents.